questions from the 5-3 homework that were asked in class. The first one I have is number 5 from 5.3. Let's see. Here we have y equals x root 8 minus x squared. And it says use the first derivative test to determine local extrema and identify any absolute extrema. All right, for absolute extrema, we have to consider the domain. X is all reals, but we cannot have a negative under the root. So I'm going to find where that equals 0. Plus or minus 2 root 2. So that means that if we are bigger than 2 root 2 or smaller than negative 2 root 2, we're going to get a negative value under here, which would make the value not in the domain. So I need to apply the first derivative test now. I'm going to pause while I get that written up. Okay, so we have our endpoints at plus or minus 2 root 2 based on the original function. Our derivative is undefined at plus or minus 2 root 2, but those happen to be our endpoints. And then I set my derivative equal to 0 and solved and got plus or minus 2. So when I set up my first derivative test, it will go from negative 2 root 2 to negative 2, negative 2 to 2, and 2 to 2 root 2. Oh, that's a lot of 2's. I pick some values, and I plug them into the first derivative, giving me a negative derivative here, positive here, negative here, showing that I have a relative min at negative 2 and a relative max at 2. Your book also says that you have a our book talks about relative extrema at endpoints, but the College Board will not ask you about relative extrema at endpoints. You can see that we would have, if we included the endpoint, we'd have a relative max at negative 2 root 2 and a relative min at positive 2 root 2. But I'm going to check the endpoints to see where my absolute extrema happen. So I look at my endpoints and my critical points, and I plug into the original function. And I got 0, negative 4, 4, and 0. So my absolute min is at x equals negative 2 and is equal to negative 4. And my absolute max is at x equals 2 and is equal to 4. Those are also relative max and min, and we will not designate endpoints as local maxes and mins. All right, so that's number 5. Let me set up the next one. Okay, on this one, they asked us to use concavity test to find the intervals where the function is concave up or concave down. So my original function was 2x to the 1/5. So I needed to get to my second derivative. My first derivative would be 2/5 x to the negative 4/5, and my second derivative would be negative 8 25ths x to the negative 9/5, or negative 8 over 25 x to the 9/5. We want to find where that equals 0 or is undefined. Well, it never equals 0, but it is undefined at x equals 0. So I set up my concavity test around x equals 0, so negative infinity to 0, 0 to infinity. Pick nice, easy test values, negative 1 and 1, and plug into, for the concavity test, we plug into the second derivative. And I get positive when I plug in negative 1, and I get negative when I plug in 1. So my interval for concave up is negative infinity to 0, and my interval for concave down is 0 to infinity. Let me move on to the next one. Okay, the next one I was asked about was number 13. We're given y equals x e to the x, and we had to find points of inflection. To find points of inflection, we have to do the concavity test, so we have to get to our second derivative. We need product rule, first times derivative of the second, plus the second times derivative of the first. And then I need to take another derivative, so I need product rule here, first times derivative of the second, plus the second times derivative of the first, plus the derivative of e to the x is e to the x. So I clean it up as x e to the x plus 2 e to the x. I need to find possible points of inflection, so I want to find where this is equal to 0 or undefined. It is always defined because e to the x is always defined as is x. So I set my second derivative equal to 0. I factor out an e to the x. I set the factors equal to 0. E to the x equals 0 never happens, so it gives us nothing. X plus 2 equals 0 gives us x equals negative 2. We set up our concavity test from negative infinity to negative 2 and negative 2 to infinity. Pick our test values, plug into the second derivative. Over here we're concave down, and here we're concave up at the point x equals negative 2, which is in the original domain. So we get a point of inflection at x equals negative 2, and we plug negative 2 into the original function to get the y. So at negative 2 e to the negative 2. So there is number 13. Okay, number 29, they gave us a graph of the position function, and then they asked us when the velocity is equal to 0 and when the acceleration is equal to 0. Well, velocity is the derivative of position, and so that's the slope of the position graph. And the slope of the position graph equals 0 at this point, t equals 0, this point, t equals 6, and I don't know, somewhere like that point, which they called 9.8. Okay? So that's when the slope of the tangent line is 0. That's when the velocity would equal 0. Then they asked when the acceleration would equal 0. All right, well, position, velocity, acceleration. Acceleration is the derivative of velocity, which is the second derivative of position. Second derivatives tell us about concavity of the original function. Well, if acceleration is the second derivative, it will equal 0 when the concavity changes sign. So if we look at, sorry, it should look a little more like that. We're looking for the places where it changes, where position changes concavity. So we're concave down all the way to about here, which they called t equals 4. We're concave up all the way to about here, which they called t equals 8. And then we're concave down to about here, which they called t equals 11. So the acceleration will equal 0 when the concavity changes sign. So that would be t equals 4, 8, and 11. I think that's number 29. Let me move on.